Welcome! In this session, we're exploring a fascinating problem, most common word. This is a great exercise for developing string manipulation skills and sharpening your algorithmic thinking. Let's dive in and solve it step by step. In this problem, you're given a string called paragraph, which represents a block of text, and a string array called band, which contains words that should be excluded from consideration. The task is to determine the most frequent word in the paragraph that is not in the band list. The solution is guaranteed to be unique, meaning there will always be exactly one valid answer. Words in the paragraph are considered case-insensitive, and the result must be returned in lowercase. For the input format, the paragraph has a length between 1 and 10,000 characters, while the band list can contain up to 100 words, with each word being no longer than 10 characters. The output is a single string representing the most frequent valid word. Let's explore examples to better understand how this works. In the first example, we have a paragraph that reads, Bob hit a ball, the hit ball flew far after it was hit, and a band list containing the word hit. After analyzing the text, we calculate the frequencies of all words as follows: Bob appears once, hit appears 3 times, appears once, ball appears twice, and so on. Since hit is in the band list, it is excluded from the results. Among the remaining words, ball has the highest frequency of 2. Therefore, the output for this example is ball. In the second example, the paragraph is just A, and the band list is empty. Here, the word A is found and has a frequency of 1. Since there are no band words to exclude, A is the most frequent valid word. Thus, the output in this case is A. This example demonstrates that even if the input is very simple, the logic still applies, and we can derive the correct result. In the third example, the paragraph is Bob. Bob, and the band list contains the word Bob. After processing the text, Bob is the only word present and it appears 3 times. However, since Bob is in the band list, it is excluded from consideration. With no other words left in the paragraph, the output is an empty string. This example highlights how the band list operates and ensures that all band words are excluded, even if they are the only words in the input. The constraints and edge cases ensure that the solution will always meet the conditions of the problem and produce a unique answer. To approach this problem, the brute force method is a simple and intuitive starting point. It involves normalizing the input paragraph by converting all characters to lowercase and removing punctuation. This ensures that the words are treated consistently, regardless of their case or any surrounding special characters. After normalization, we split the paragraph into individual words and count the frequency of each word using a dictionary, also called a hash map. Once we have these frequencies, we exclude any words that are part of the band list. The final step is to identify the word with the highest frequency among those that are not banned. This approach works well because normalization handles case sensitivity, and removing punctuation ensures we only process actual words. Using a hash map is efficient for counting frequencies as it provides quick lookups. However, the trade-offs include multiple sequential steps, such as cleaning the string, iterating over words, and maintaining the dictionary for frequency counting. The runtime performance of this approach depends on the size of the string and the number of unique words, and in cases with many words, dictionary operations could become a bottleneck. When analyzing the brute force method, its time complexity is O, n plus m, where n represents the number of characters in the paragraph, and m is the number of unique words. The space complexity is O, k, where k is the number of unique words. To improve efficiency, we can adopt an optimized approach that simplifies the process and reduces manual steps. In this approach, Python's collections counter is used to count word frequencies directly, eliminating the need for manually updating a dictionary. For text normalization and punctuation removal, we use regular expressions, or RE, to handle these tasks in a single step. By storing the banned words in a set, we ensure that checking if a word is banned occurs in O1 time. Finally, the most frequent non-banned word is found using Python's max function, which directly retrieves the key with the highest value. This approach is more concise, leveraging built-in Python libraries for optimized performance. The use of regular expressions simplifies text processing, and sets provide efficient lookups, making the solution both elegant and effective. In the optimized implementation, we first use the reFindAll function to normalize the paragraph by converting it to lowercase and extracting words while ignoring punctuation. The banned words are stored in a set to allow for fast lookups. Then, we use collections counter to count the frequency of each word, excluding any words found in the banned set. This ensures that only valid, non-banned words are considered. Finally, we use the max function to identify the most common word based on its frequency in the counter object. The chosen method stands out for its conciseness, as it relies on Python's robust libraries to handle the heavy lifting of text processing and frequency counting. The time complexity remains n plus m, as we still process each character in the paragraph and count unique words, but the code is significantly more readable and scalable compared to the brute force approach. The space complexity also remains k, consistent with the earlier method. While regular expressions can sometimes be slower for very large strings, this trade-off is usually negligible given the efficiency gains in other areas. In evaluating alternative approaches, we considered manually parsing the paragraph for normalization and punctuation removal. However, this would increase code complexity and reduce efficiency. Another alternative was sorting the frequency dictionary to find the most common word, but this introduces an additional k log k step, which is less optimal than using max for direct retrieval. The chosen strategy strikes a balance between simplicity, performance, and readability. By leveraging Python's built-in libraries, such as re, counter, and set, we streamlined the solution, avoiding redundant computations and reducing the likelihood of errors. The key insight was recognizing how these tools could be combined to handle text processing, frequency counting, and banned word filtering in a highly efficient manner. This approach ensures the solution is not only performant but also easy to understand and implement, making it an ideal choice for this problem. To solve the most common word problem efficiently, the first step is to normalize the input paragraph. This means we convert all the text to lowercase to ensure that words like apple and apple are treated as the same, which eliminates case sensitivity issues. Next, we remove all punctuation marks using a predefined character set like string.punctuation in Python. This ensures that punctuation such as commas, periods, or exclamation points doesn't interfere with word matching. For example, the input hello world. This is a test would become hello world this is a test. After normalization, we tokenize the paragraph by splitting it into individual words. This is done using the split method, which separates the string by whitespace and produces a list of words. For instance, the normalized string hello world this is a test would be split into the list hello world this is a test, making it ready for further processing. Once we have the list of words, the next step is to count how many times each word appears. To do this, we use a dictionary, which is an efficient data structure for storing key-value pairs. Each word in the list becomes a key, and its frequency becomes the value. As we traverse the list, we check if the word is already in the dictionary. If it is, we increment its count; if not, we add it to the dictionary with an initial count of 1. For example, given the list, hello world, this is a test, hello, the resulting dictionary would be, hello, 2, world, 1, this, 1, is, 1, 1, test, 1. With the frequency dictionary built, we then identify the word with the highest count. This involves traversing the dictionary and comparing each word's count to a running maximum. For instance, from the dictionary, hello, 2, world, 1, this, 1, is, 1, 1, test, 1, the word hello would be identified as the most frequent word with a count of 2. It's important to anticipate edge cases to ensure the algorithm works reliably. For example, if the input is an empty string, the algorithm should return an appropriate response, such as none or an empty dictionary. Similarly, if the paragraph contains only punctuation or special characters, normalization might result in no valid words, and this case should also be handled gracefully. Another key edge case is when 2 or more words have the same highest frequency. In such scenarios, the algorithm should return the word that appears first in the paragraph based on the order of traversal. Now, let's delve into why we take specific steps in the algorithm. Normalizing the input by converting it to lowercase and removing punctuation ensures that we compare words consistently, avoiding mismatches caused by trivial differences like capitalization. Using a dictionary to count word frequencies is particularly useful because it provides constant time complexity for inserting and looking up keys, making the process both fast and scalable. When determining the word with the highest frequency, we traverse the dictionary in a single pass. This approach is efficient because it avoids unnecessary computations and ensures the overall algorithm remains fast. By leveraging the frequency dictionary, we only need one additional pass to identify the most common word, which keeps our time complexity low. Now, let's examine the data structures used in this solution. The dictionary, or hash map, is central to the algorithm. It stores words as keys and their frequencies as values, and it's highly efficient because it supports fast lookups and updates with an average time complexity of 1. Additionally, we use a list to store the tokenized words from the paragraph. Lists are simple, lightweight, and easy to traverse, which makes them ideal for this stage of processing. Finally, let's analyze the complexity of this algorithm. For time complexity, normalizing the paragraph requires n time, where n is the length of the paragraph. Tokenizing the string into words also takes n. Counting word frequencies involves traversing the list of words, which takes m, where m is the total number of words. Finding the most frequent word involves a single traversal of the dictionary, which takes k, where k is the number of unique words. Combining these steps gives an overall time complexity of n plus m plus k, which simplifies to n, in most cases since the number of words in unique words is typically proportional to the length of the input. For space complexity, the dictionary requires k space to store unique words and their counts, while the tokenized list needs m space for all words. Thus, the total space complexity is m plus k. This balance of time and space efficiency makes the algorithm robust and practical for solving the problem. The given solution efficiently solves the problem of finding the most common word in a paragraph, excluding a list of banned words. Here's how the code works. The first step is to normalize the input paragraph. To ensure uniformity in word representation, the code converts all characters to lowercase and replaces any non-alphanumeric characters, like punctuation, with spaces. This is done using a generator expression and the Python join method, which iterates through each character in the paragraph. If the character is alphanumeric, it is converted to lowercase, otherwise, it is replaced with a space. Next, the normalized string is split into a list of words using the split method. This step ensures that all words in the paragraph can be processed individually. The banned words are stored in a set for faster lookup. Using a set allows 1 average time complexity for membership checks, which is more efficient than using a list. The counter class from the collections module is used to count the occurrences of each word in the list of words. A generator expression is passed to the counter, which filters out any words that are present in the banned set. This ensures that banned words are not included in the frequency count. Finally, the most _common method of the counter object is used to retrieve the most frequent word that is not banned. This method returns a list of tuples, where each tuple contains a word and its count. The 0 indexing retrieves the word from the first tuple, which is the most common word. This approach is efficient, with a time complexity of n, where n is the number of characters in the paragraph. The space complexity is also reasonable, as it primarily depends on the size of the paragraph and the number of unique words. Overall, the code is concise, well-structured, and handles edge cases like punctuation, case sensitivity, and banned words effectively. Here, we start by normalizing the input paragraph. This involves converting the entire string to lowercase to ensure case insensitivity and replacing any punctuation with spaces so that we can focus solely on the words. Next, we split the normalized paragraph into individual words using the split method with the regex_s+, which handles multiple spaces. After that, we create a hash set to store the banned words, as sets allow for efficient lookups. Then, we initialize a hash map called wordCount to keep track of the frequency of each word that isn't in the banned set. For each word in the array of words, we check if it's not in the banned set. If it's not banned, we update its count in the wordCount map using the getOrDefault method, which simplifies incrementing the count. This structure ensures we have a record of all valid word frequencies. Once we've populated the wordCount map, we need to find the most common word. To do this, we iterate over the entries in the map. For each entry, we compare its value, which represents the word's frequency, with the current maximum count. If the frequency is greater than the maximum count we've seen so far, we update most common to this word and set max count to this new frequency. After the loop completes, we return the word stored in most common, which is the most frequently occurring word that isn't banned. This approach ensures both clarity and efficiency in determining the result. To solve this problem, we start with a paragraph and a banned word, and our goal is to determine the most common word that is not banned. First, we normalize the paragraph by converting all characters to lowercase and replacing punctuation with spaces. This ensures consistency in the text by removing case and special characters as factors. The result is a clean string where all words are lowercase and separated by spaces. Next, we split this normalized string into individual words, using spaces as the delimiter. This gives us a list of words that we can work with. After that, we convert the banned word list into a set. Using a set allows for faster lookups, which is important when filtering out banned words in the next steps. Now, we count the frequency of each word in the list, excluding words that are in the banned set. This means we iterate over the words and keep track of how many times each word appears, but we skip any word that is banned. The result is a dictionary where the keys are words and the values are their respective counts. Finally, we extract the most common word by finding the word with the highest count in this dictionary. In this example, the word ball has the highest frequency of 2, making it the most common word that is not banned. The final output is ball. In this example, we are given a paragraph with no banned words. We begin by normalizing the paragraph, just as before, converting all characters to lowercase and replacing punctuation with spaces. This gives us a clean, lowercase string. Then, we split this string into words, creating a list of words that we can process. Since the banned list is empty, we convert it into an empty set. This means no words will be excluded during the counting step. Next, we count the frequency of each word in the list. Here, every word appears exactly once, so the resulting dictionary shows a count of 1 for each word. Since all words have the same frequency, the solution returns the first word in the dictionary as the most common. In this case, that word is a. The final output is a, as it is the first word with the highest frequency. In this final example, the paragraph contains a few words, but all of them are banned. After normalizing the paragraph by converting it to lowercase and replacing punctuation with spaces, we split the string into a list of words. Then, we convert the banned list into a set for efficient lookups. At this point, we count the frequencies of words that are not in the banned set. However, since every word in the paragraph is banned, the resulting frequency dictionary is empty. As there are no valid words left, the output is either none or an error, as no word meets the criteria for being the most common non-banned word. To analyze the time complexity of this solution, we start by breaking down the various steps involved. First, we normalize the paragraph. This involves iterating through each character of the input string, checking if it's alphanumeric or not. Since this operation processes every character one by one, its time complexity is O(m), where m represents the length of the paragraph. Next, we split the normalized paragraph into individual words using the split method. This operation also takes O(m), since it scans the entire string to identify word boundaries. Finally, the banned words, provided as a list, are converted into a set. The conversion of a list with b elements into a set takes O(b), as it requires processing each banned word. Each of these steps contributes to the overall time complexity of the function. Now, let's evaluate the steps that involve filtering and counting the words. Using a generator expression, we filter out words that are present in the banned set. Checking membership in a set is an O(1) operation on average, and since this is repeated for each of the n words in the list, the total filtering step takes O(n). After filtering, the collection's counter object is used to count the frequency of each word. Counting n words also takes O(n) on average, as each word is processed once. To find the most common word, the most_common 1 method is used. While this method sorts the frequencies internally, finding just the top result is effectively O(n), given the number of unique words. Combining these steps, the dominant terms in the time complexity are O(m) for normalization and splitting, and O(n) for filtering and counting. Thus, the overall time complexity for the solution is O(m plus n plus b). Switching to space complexity, the memory usage depends on the intermediate data structures created during execution. First, during normalization, a new string of length m is created, requiring m space. Next, splitting the paragraph into words results in a list of n words. If the average length of each word is k, the space required would technically be n*k. However, since these words come directly from the original paragraph, this is bounded by m. The banned words are stored in a set, which requires b space for b elements. Finally, the counter object stores the frequency of each unique word. If there are unique words, this requires u space. Since u is at most n, this contribution is bounded by n. Combining these terms, the total space complexity is m plus b plus u. Finally, since u, the number of unique words, is bounded by n, and m is the dominant factor, the space complexity simplifies to m plus b. Comparing this approach to a naive solution, where each word might be manually checked against the band list and frequencies counted using nested loops, we see a clear improvement. A naive approach would have a time complexity of n*b, which is significantly slower than the optimized solution. By leveraging efficient data structures like sets for banned word lookups and the counter object for frequency counting, we significantly reduce redundant computations. In summary, the optimized solution achieves a time complexity of m plus n plus b, and a space complexity of m plus b, making it far more efficient than its naive counterpart. When working on this problem, there are several common mistakes to watch out for. One of the biggest pitfalls is failing to normalize the input properly. This means not converting all strings to lowercase or neglecting to remove punctuation, which can result in mismatches when comparing words. For example, hello and hello would be treated as two separate words if normalization is skipped. Another issue arises with how strings are split. Using split, instead of the more robust split, can cause problems if the input contains extra spaces, as split handles multiple spaces more gracefully. It's also important to consider edge cases, such as an empty paragraph, repeated banned words, or inputs consisting only of punctuation. Overlooking these scenarios can lead to incorrect results. Additionally, the choice of data structure matters. For example, using a list to count word frequencies can lead to inefficiencies due to slower lookups compared to dictionaries or collections counter. Finally, some beginners tend to overcomplicate their solutions by using nested loops or redundant data structures, which can lead to suboptimal n² complexity instead of the desired n. Keeping these issues in mind will help you write cleaner and more efficient code. Now, let's think about how this problem is approached in an interview setting. Interviewers often test your ability to handle edge cases. For example, can your solution manage empty paragraph inputs, a lack of banned words, or strings that only contain punctuation? Optimization is another key area. While a brute force approach may demonstrate an understanding of the problem, interviewers typically expect you to optimize your solution by using efficient algorithms and data structures, like hash maps. It's also important to communicate trade-offs when discussing alternative solutions. For instance, you might highlight why one approach is better for readability, while another excels in performance. Recognizing the underlying patterns is critical too. This problem often tests your skills in string manipulation and frequency analysis, which are techniques that commonly appear in other problems, such as identifying duplicates or finding anagrams. These insights can help you make a strong impression during an interview. This problem connects to a variety of related problems that involve similar concepts and techniques. For instance, in LeetCode 49, Group Anagrams, you work on grouping words that have the same characters. This requires advanced string manipulation skills, much like this problem. Another example is LeetCode 242, Valid Anagram, which asks you to determine if two strings are anagrams by analyzing character frequencies. LeetCode 451, Sort Characters by Frequency, is another related challenge, where you sort characters based on how frequently they appear, applying frequency analysis in a different way. Lastly, there's LeetCode 290, Word Pattern, which tests your ability to match patterns within strings, a task that also often involves hash map manipulation. Exploring these problems can help deepen your understanding of the techniques used in this problem and build a solid foundation for tackling similar challenges. There are several approaches to solving this problem, each with its own trade-offs. A brute force approach involves using nested loops to manually count the occurrences of each word. While this method is straightforward, it's inefficient, with a time complexity of O(n) squared, due to the repeated iterations. A more efficient option is to use a hash map to count word frequencies. This approach has a time complexity of O(n) and allows for quick lookups and updates. Another option is sorting based. You first count the word frequencies and then sort them in descending order of frequency. This method works but introduces additional overhead, as sorting increases the time complexity to O(n) log n. Finally, Python's collections counter provides a concise and powerful way to handle frequency counting. It simplifies the code significantly while maintaining an efficient O(n) complexity. Choosing the right approach depends on the context, but leveraging tools like counter can often lead to cleaner and more effective solutions. Great job! Today, we reviewed the most common word problem and learned how to use hash maps for efficient text analysis. Remember, these techniques are not just for this problem but can be applied widely in string-related challenges. Keep practicing, and don't forget to like, share, and subscribe to stay updated with more problem-solving sessions. Thank you, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!